Hello everyone, my name is Yuan Ming. As you can see from the title, my topic is custom purpose parser versus general purpose parser. Here's the table of content. And I'll start with the general purpose parser, GPP, and introduce 5 types of them. Then I'll go to custom purpose parser, ASSP. This is short for application specific system parser. I'll give an example on it, go through the steps of modeling a ASSP, and then at the end I'll briefly talk about the optimization method. GPP. So GPP is designed for general purpose computers like PCs and workstations. Typically there are 5 types of GPP, and I will talk about each one of them briefly. Microprocessor, it is a GPP that is similar to CPUs because both of them have a control unit and ALU and also a bunch of registers. For the microcontroller, it is basically a computer with various packages and sizes. And as the name shown, it is used for controlling the external electrical devices like micro SD card and sensors. If you look at the microcontroller, you'll notice that there are a lot of input and output pins on it. So microcontroller is also called general purpose input output, GPIO. For the embedded processor, it is designed for mechanical functions and electrical functions. It usually consists of various blocks like timers, interrupt controllers, program memory, and so forth. Digital signal processor is designed for measuring, filtering, and also compressing the digital and analog signals. So as the figure shown, this is the general process of DSP. There are going to be an input coming in, and DSP will convert it from analog to digital signal. Then it will do something with it. Let's say a high-pass filter. After that, DSP will convert it from digital back to analog, and that will be the output signal. That's the general procedure. Finally, media processor is pretty simple. It is used for processing the images and videos, and that's it. Custom purpose parser. So I mentioned in the previous slides that it is used for a specific application. Because of that, it is usually fast, small, and has lower power consumption compared to the general purpose processor. But because of its customization, it also has a higher NRE, which stands for non-recurring engineering. This means that custom purpose processor would take more time and also more money to develop. And also it has a longer time to market and also less flexibility. So now I'll go through some steps of developing a custom purpose parser. The example I gave is the greatest common divisor, GCD. So I believe some of you might have written some code or seen the code in other courses for the GCD, and here is shown in the figure B. And that's our very first step. We're going to create an algorithm for GCD. After that, we are going to convert this algorithm to the finite state machine with data path, FSMD, which is shown on the right of the slide. So if you look at it, there are a bunch of states, and there are like if you compare both, if you like looking at both the pseudocode and also the state diagram, you will notice that there are a lot of similarities because they are doing the exact same function. They has the exact same functionality. So there's an if else statement. It is represented as the branching on the right, and also there are two while loops. One is at the top, one is at the bottom here. Next, we are going to create the data path. So the very first thing is to create a register for each variable, because the values of the variable will be updated, and also create a function unit for each arithmetic operation, and connect the ports register and functional units. This is the state diagram in the previous slide, and now we're going to have a data path block. All of this arithmetic operation will be controlled by the controlling signals, which will be talked about in the next slide. So this block basically consists of different arithmetic operations, and there are the comparing units, the not equal, smaller, and also to subtraction, which is state 8 and state 9 to the subtraction. So all of this will be controlled by the controlling signals. Now we are going to create the controller's FSM. This is really similar to FSMD, but we are going to replace the complex conditions with data path configurations. So you will see that all of this arithmetic operations is replaced by the controlling signals, which will be sending to those subtractor units and also the comparator. And also this is similar to what we did in digital design. We're going to name the states in binary representation from 0000 all the way up to 1100. Finally is the controller and data path. So we have the controller is shown in the figure on the left. It has a combinational logic and also all the controlling signals that will be sent to the figure on the right. And it has a state register that it will keep updating the states of this processor based on the signals from the right. If we look at the combinational logic, we already know that it is consists of lots of logical gates like AND gate, OR gate, XOR gate, and that's where the VLSI comes into play. Here's the controller state table for GCD. It's like a huge table, so I will not go through the detail. But if you look at all the signals, this Q is the current states, and this I for I3, I2, I1, I0 are the next states, and the rest are just the controlling signals that will be standing back and forth between the controller and also this data path block. Now we are going to talk about how to like optimize the custom purpose processor. The very first thing is to analyze the program attributes and seek possible improvements. Those improvements include number of computations. If we could like lower that number, the processing time will be less. And also the size of the variable, like we could minimize the size of register to save some space. And also the operation used. Let's say we have a multiplication and division. If we could replace it with the addition or subtraction, which is normally less expensive than the previous two, we overall optimize our processor. So here is one of the optimization method that is applied on GCD, and the one that is applied is reducing the number of computations. And if we look at the original program, we could like write it in another way with the exact same functionality. So both of these programs has the exact same functionality. If we look at the down, the one on the left goes through 9 iterations with the input of 42 and 8, and each of the iteration is shown at the bottom. But the one on the right, which ends up to have more code, but it only need to go through 3 iterations to complete the calculation with the exact same input. So by comparing both programs, the one on the right ends up to be faster because there are like fewer iterations, but it ends up to have more lines of code, which means there are more states. The states register will be larger. The combinational logic will also be larger, and also we will have another register to store the variable r. So this is the design trade-off between the delay, the overall processing time, and also the space and cost of designing the processor. That's the end of my presentation. There are a total of 2 references that I use for these slides, and that's it. Thank you.